Hello, this is the video where I'm going to work out questions from Unit 5, Module 1B. This has many of the questions from the homework. They're all taken from the homework, and then I elaborate on different aspects of the problem. You're going to have problems similar to this in your exam 1B. Okay, so the question here is about ionics. We want to know which of these substances, ionic substances, have a +2, -2 charge. Okay, as we mentioned in class, when we look at the periodic table, you're expected to recognize some of the landmarks, general trends. And if we look at the first two columns, the first column is +1, and the second column is +2. So lithium, sodium, potassium, rubidium, those are always going to be +1. Magnesium, calcium, strontium are always going to be +2. Then we have in the middle of the periodic table a big mystery zone. And then we get to the last two columns and we have a very similar trend, but now they're with negative numbers. So fluoride is -1, chloride, bromide, iodide. And then we have oxygen, sulfur, and selenium. So -2 and -1. So these are the ions you're expected to be able to recognize from the periodic table. Okay, so what we're going to do, there are, as I mentioned in class, there are some polyatomic ions that you're expected to know. There's no way to know these charges without memorizing them. So we have nitrate that has a -1 charge. Okay, there we go. Whoops. Oh, no. There we go. And then we have sulfate, which is FO4 2-. Let me see if I can. I'm sorry. I didn't know I was going to click that button. I didn't mean to. Okay, so I'm just going to, you can step forward back to where we were. I'm just going to go over to it. So these are the common cations and anions that you're expected to know: +1, +2, -1, and -2. And then we have our polyatomics that you're expected to know. -1 is nitrate, sulfate, SO4 2-, carbonate, CO3 2-, phosphate, PO4 3-, and hydroxide, OH-. Okay, so those are the ones we're supposed to know. Now let's take a look and see, are any of these ionic substances +2, -2? All right, well, magnesium we see is on our table from the periodic table, Mg2+. Sulfide is right below oxygen, and that's going to be 2-. Calcium is 2+, same category, same column as magnesium. Oxide is 2-. Potassium is +1. Nitrate, NO3-, is -1. That's a polyatomic ion. Sodium ions +1. Oxygen is -2. So based on that, the correct choice here would be A and B. Keep in mind there's one more polyatomic, the 6th polyatomic. It has a positive charge that you're expected to recognize, and it's ammonium, NH4 +1. It's the only one that's positively charged that you're expected to know. Are these the only 6? No, but these are the only 6 we require that you recognize by name and formula. Okay, so we did a problem like this in class where we're going to rank the energetic stability of ionic substances. All right, so energetically stable, the most energetically stable is going to be the lowest potential energy. Right, the lowest potential energy. Most negative. And then the highest potential energy going to be the least negative, least stable. All right, so what we mentioned in class is we're going to need to know the charges of each of the ions. So sodium is +1, oxide is -2. Magnesium is +2, oxygen's -2. Calcium is +2, oxide is -2. So those were all in the analysis we did on the previous slide. And now we have a mystery, titanium. That wasn't in our 2 columns of metals. So we have to figure that one out. So titanium plus 2 oxygens, each one at -2, must sum up to be 0. Right? Remember, 0 is the total charge here. Solving for that, titanium is +4. So now that we have all of the oxidation states, we can now calculate the potential energy. Okay, so let's do that. Remember, the potential energy is equal to the first charge times the other charge over size. Okay, that's our formula. All right, so +1 times -2 is -2. +2 times -2 is -4. +2 times -2 is -4. And +4 times -2 is -8. Okay, so we see we have a pretty natural grouping. We have 1 -2, 2 -4s, and 1 -8. Now what we want to do is rank their potential energies. All right, so we have -2, -4, and -8 here. And now we're going to put the first one here. This is the weakest interaction, right? It's got the highest potential energy. And now we have 2 of them at -4. As we did in class, because of the size that's in the denominator, the bigger one always has weaker interactions because the ions are farther apart. Farther apart the ions, the weaker the interaction. That is a general rule for potential energy. Then we go down to, so that means the smaller ion, which is magnesium. And remember, where do we get that from? If we're looking at column 2, we see beryllium, magnesium, and calcium, right? So we go up a column, get smaller, there's less electrons. This is the shell model. As you go down a column, it gets bigger. Okay, so that's what we're doing. So the ions are getting bigger, the interactions are getting weaker. And then the final one is titanium at -8. So that's how we would rank the potential energy for this system. It would go weakest, then calcium oxide, then magnesium oxide. At the very bottom, the most stable would be titanium oxide. All right, so that's it for ions. Those are the questions we asked. And now we're going to ask you about delta H and delta S. So what are the correct answers? There's 2 of them with these signs of change. All right, so what we're going to do is break down the change. Delta H less than 0, delta S less than 0. Okay, so what's that mean? So delta H less than 0, it's a negative value, and that means we must be starting high and ending low. That's how we get a negative change. So that means the products have the lowest quantity. So whatever the change, if the change is negative, products will always have the lowest quantity. If we look at delta S, that's negative. All right, we get the same graph. It must start high for reactants and low for products. All right, so the first thing we can do is now identify, okay, so A, the entropy of reactants is higher. True. If delta S is negative, you must start high in reactants, go low products. So the entropy of the reactants is higher. C is also true. The products have the lowest potential energy because the delta H was given to us as negative. Just keep in mind that for energy, the favored state is the lowest potential energy. For entropy, it is the highest number of configurations. The highest entropy is favored. Alright, so now how do we get the signs of delta S? So the rest of this video is about assigning entropy and energy and making sure we get the right signs. Alright, so this question is in the homework and it says we want to order the entropy. Alright, so as we talked about in class, the primary consideration for entropy is phase. We count gas particles. So the greatest number of gas particles will always have the highest entropy. Then it's liquid, then it's solid. Okay, so we don't see any gas particles, so we're going to ignore that and say, okay, for entropy, right, remember this is entropy, I know it says S, which can get confused with solids. So for ranking entropy, we put liquids on top and solids on the bottom. And now within the phase, our secondary consideration is mass. So we're going to put the highest mass at the highest entropy within the phase. Lowest mass, right? Same here, solid, highest mass, lowest mass. Okay, so that would be our ranking. And so that means we need to know the masses. So what we're going to do is just add up the molecular mass here. So we do that for C2H5OH ethanol, and we get 46 grams per mole. Magnesium hydroxide, keep in mind you got to distribute the 2, 59 grams per mole. Calcium hydroxide, 74 grams per mole. And then methanol is 32 grams per mole. Oops, sorry, I wrote over it, but we'll see it soon. Okay, so the lowest mass solid is magnesium hydroxide. The next highest mass solid is calcium hydroxide. So these are the low. So we're starting the lowest entropy. You always see the recipe, right? For the lowest entropy is a solid lowest mass. Okay. Then we go up to the liquids, and so the lowest mass liquid is here. Highest mass liquid is going to have the highest entropy. So the highest entropy, since we don't have any gas particles, is going to be the liquid with the highest mass. And that would be our ranking. Alright, so now what we want to do is use those rules to assign changes in enthalpy, changes in entropy, and apply them to energy and path diagrams or energy and configuration diagrams. Keep in mind this is the same as H and S, right? H and S are the same graphs. So let's go through how we would analyze this problem from the standpoint of energy, standpoint of entropy, and pick answers. All right, so from the potential energy standpoint, we have a phosphorus-phosphorus bond plus a hydrogen-hydrogen bond going to phosphorus-hydrogen bonds. Okay, so based on this analysis, we'd have a high AABB. These are high potential energy bonds going to stronger, polar, shorter AB bonds. This is the kind of rationale we'd expect you to use here. Lower potential energy, stronger bonds, they're shorter, they're polar bonds. Okay, and with that we would get this analysis. Products have lower potential energy. So let's look at the entropic analysis. We have a solid plus 6 gas particles, making 4 gas particles. Okay, so with that we can then say we're going from high entropy. Why high? Because there's more gas particles here. 2, and that's favored, to less gas particles. Why? Because there's only 4. And so we're going from high to low in both. That means delta H, which is the same as change in potential energy, is negative, high to low. Delta S is also going high to low, and it's negative. right? They're both less than 0. Right, so now we can pick the graphs associated with this analysis. So if we take a look at the entropy, we have low to the left, high to the right. And then we see this case that reactants have high entropy. That's true in A. And reactants also have high potential energy, which is also true for A based on our potential energy. So our products are at low potential energy, low entropy, right? And we pick A. If we look at the reaction path, well, we can immediately cross out A and D because they have the reactants and products switched. And now the question is, do we have an exothermic reaction, which is B, or an endothermic reaction is C? And the answer is B. Keep in mind that the reaction path diagram ignores the analysis of entropy. So you only use entropy when you have configurations as your x-axis. All right, so what we're going to do is analyze these three reactions for energy, for entropy, and make the corresponding H versus S curve. All right, so let's do that. H versus S and delta H and delta S. Okay, so we're going to do each of them. So let's ignore B and C. Right, so we start with carbon and oxygen reacting to make CO2. That means we have carbon-carbon bonds plus OO bonds going to CO bonds. So just like before, in that case, we have high to low. Delta H is less than 0. If we go to the entropic argument, it's a more interesting case. We have solid plus gas making one gas. We ignore the solid here. And now we need to use secondary considerations because we have the same number of gas particles on both sides. So we have low mass gas going to high mass gas. So that means we're going from low to high. Low mass gas particle to high mass gas particle. That means delta S here is positive. So we have delta S is positive, change in entropy is positive, products have more entropy, and an exothermic reaction. All right, so I'm going to show you how I build H versus S curves. The first thing I do is I put in dash mark the entropic product. So I kind of start what's at high. So I look at high here where the product is, and the product is at high entropy, so I draw it to the right along the dashed line. And then based on energy, I know products are low, so I just put the final state of the products now in the bottom right. That means the reactants go to the top left. Reactants are high H and low S, right? So that's how we would build that curve. Okay, we just did the first one. We're going to ignore the third one. Let's do B. All right, so same thing, HS and H versus S. So potential energy here, we have CH bonds making CC and HH bonds. Then we have low potential energy reactants, high potential energy products, right, based on the bond strengths, low to high. And if we're going low to high, the change is positive, right? Delta EP, delta H are now positive. If we look at entropy, now the story, remember the change in S here, is one gas particle is going to a solid plus two gas particles. Remember, we just ignore the solids. Low entropy at one gas going to high entropy at two gas particles, low to high. This is also positive, so we have positive, positive. So the products have the highest entropy, so I'm going to write that as the dash line to the right here. And then, because I know the products also have the highest potential energy, I'm just going to dash up to the top here and write my final product. that also means that my reactants are now at the lowest energy, lowest entropy in the bottom left. Right? So you really want to get in, you don't want to do all this analysis correct and then pick the wrong diagram. So carefully pick the right one, and that will help you. All right, so last one, we're going to do C. All right, so let's do C, potential energy story. CO bond plus an OO bond makes CO bonds. So there's going to be high potential energy to low. Keep in mind the weakest bond is in the reactants. We have AB bonds in both reactants and products, but the only AA bond is in the reactant. Okay, so now we go high to low. Delta H is less than 0, negative. We look at the entropic story. We have 2 gas particles plus 1 gas particle making 2 gas particles. That gives us high to low. High entropy reactants going to low entropy products. High to low also means delta S is less than 0. So they're both less than 0. What we're going to do is analyze this as, okay, let's put the products at the low entropy side now. And then from here, we're going to say, look at the energy. Energy is low for products, so we put our final products down at the bottom, low entropy. And that also means that our reactants are at high entropy and high energy, which should be in the top right. Okay, so that is the review for our homework, Unit 5, Module 1B. Good luck.